Swayam Prabha. Digital India. Educated India.
Just a small. I need a bit of help if possible. It would be really great. So, it's really fantastic to learn about this stuff, but it's just maybe it's my personal opinion, but sometimes I struggle to keep up with you. So, it would
Is
be
it
nice
okay?
to just give a quick summary of some things, right? Because
Sure.
sometimes it gets a little hard to keep up.
Okay, no problem. Yeah, yeah. Just let me know where to stop or slow down, or like if you have some questions. Yeah.
Sure. Thank you.
Okay. Yeah. So yeah, let's get started with this second session. So in the morning we looked at kind of the origin of hypervisors, the history of them, and then why virtualization came to be so important. And we looked at VMM architectures and some of the requirements from the seminal specs from seminal papers from Popek, Goldberg, and Popek. And we looked at x86 architecture in brief. I think we looked at the things which are important to virtualization. I think the privilege rings and the segmented memory and the paging architectures. And we looked at some of the challenges in x86 processors in virtualization because um, I mean, in a typical OS application architecture, you would run just the OS in ring 0 and the application in ring 3, and things would be fine. Everything would trap, and the OS can emulate wherever there is a conflict. But in a virtualization kind of situation, I think it becomes a challenge for x86 processors since 1 and 2, the ring levels 1 and 2 are not really used for paging. So that becomes a challenge. So it's basically a supervisor mode and a user mode as far as paging is concerned. Plus, there are some challenges with some of the instructions where uh, the implementation is such that if you run the OS kernel in a ring 3, the same as the application, then you have a challenge, and uh, you will either there will be some leakage of information, or some instructions won't run properly. Some of the memory architecture is difficult to kind of track because the OS can go and change page tables on its own, and the VMM will not be aware of some of those things. So those are a few of the challenges which we saw in x86 processors. And so when VMware Workstation they started the work, I think they with the 32-bit x86 architecture, I think the initial thoughts were on doing handling these with software techniques. And one of the oldest software technique for CPU virtualization was binary translation. So we'll go into that now. So binary translation, I think if you're aware, if you've studied some of it in your engineering, you will know that basically it involves taking a binary and then translating it either to maybe run on a different architecture, or maybe if you want to do some optimization around the binary, and then you can make modifications in the binary in the final assembly, and you can run it on the system. So that's what a translator basically does. A dynamic binary translation does all of this on the fly. I mean, it's while things are on the fly, it just reads from the binary, keeps reading as it runs. It keeps parsing it. It keeps optimizing it, generating the low-level IR intermediate representation of it, and then translating it to the architecture which it wants to. So it could do a cross kind of compilation also. It could do across platforms. For instance, it could read an x86 binary and then run it on an ARM processor, for instance. So that's a basics of a dynamic binary translation. And so in this case, it would read the binary. It would do parsing, like I said, optimization, low-level optimization, and then it would kind of maintain it in a code cache. I mean, the translated code, and it would also maintain tags to um, basically in code you have things like jumps and branches and things like that. So it has to maintain metadata information to know where it has to branch to, because the code structure as such is not maintained once you do a dynamic binary translation. So since it's getting translated, uh, the overall look and feel of the code will kind of change, and so you can't branch to the same addresses if it's a branch to an address which is there in the original code. So you have to kind of branch back to the decoder, which then figures out how to branch to the next location. So there is a presentation by Joel Emmer from MIT, from which I took this particular slide. I was hoping there would be a paper on this, but there was no paper on this. But it's a good slide to kind of show what's happening. And then so basically the tags help in kind of uh, relocating the code based on branches and things like that, and then it goes back to the decoder, and then it tries to decode the next block of instructions. So that's how a DBT works. So what VMware did was, I think they used binary translation of the code, because they were running uh, they had two kind of ways they ran the code on x86. So they ran it as 013 as well as 033, in the sense that the VMM would run at ring 0, the OS kernel would run at either ring 1 or ring 3, and the OS application would run at ring 3. So in the initial days, I think they ran it with 013 when it was a segmented kind of architecture. And when they went to 64-bit, I think they went to a 033 kind of architecture. But then I think the way they had to solve all these problems where the code would not run properly, or would have some kind of information leaks, is that they used binary translation. So basically what the VMM would do is it would read in the original x86 binary, including the OS and the applications from disk, and then it would do a translation dynamically on the run, on the fly kind of thing, block by block, to be able to run. So some of the code it can run in direct execution mode. So it would just do as kind of a scan parse of the code to figure out if it needs to do a translation or if it can just run identically. So here, I think this is another very nice paper by Keith Adams and Ole Agison. I think both of them are from VMware, and this is one of the excellent papers I've seen on binary translation, which they've written in 2006 in Operating Systems Review. And they took an example of a small function of is prime, basically, and then they showed how binary translation would work. So on the right hand side, you see the x86 code which would be generated for is prime. And with binary translation, what you would do is you would take this code and then you would basically segment it into kind of blocks, and then try to do a translation of it to the architecture. In this case, to x86 architecture itself. So it was the same architecture, same ISA. So in terms of the basic blocks, I think most of the instructions would be copied identically. Where there are privileged instructions, they have to kind of emulate it. And that is where I think the VMM code running in a separate uh, kind of address space helped, because they can actually do um, the translations in that piece of code. And then they had a decoder, and they had these code tags to be able to do the branches inline. And so if you see the two blocks here, I think they've taken the first block, and then it's identically translated. And then at the end, I think when you have the jump, you see that they have to actually make sure that they can't really jump to the same location, because it's an address which is not at the same location. So they have to jump back to the binary decoder. And so in the first time when this code is running, so they given in this paper, they give an example of is prime of, let's say, a number like 49, which is a prime number which is running. And so when it runs the first time, it would actually branch back to the decoder, and then it would branch again to the next block, or fall through in case if the jump is not taken, for instance. So this is the code below is the actual translated version of it. And then, so like I said, they give an example of is prime 49. So they, if you keep running with prime numbers, then the code gets into the cache, in the sense that wherever they are doing the jumps back to the decoder and back to the next piece of code, they can actually kind of circumvent that whole flow, and they can just branch directly to the cache itself. So that's what they do, I think. So if you keep running a piece of code, I think they have enough. They have a huge code cache, and they run it basically within the code cache. And wherever there are privileged instructions, they would do the translation. The other thing which you see in this thing is, I think they use GS register. So like I said, GS is a register which is not used by typically by the operating system. So in this case, they use it to kind of spill over. So if they have a register which they want to use for some reason, they would spill it over to their VMM memory using the GS prefix. And then they would use that register as required, and then uh, take the register back from memory, and then spill it back, and then start using it again. So that is the way they implemented dynamic binary translation on VMware. So this was I think a pretty effective technique. I think if you see the paper also, I think I think this and another paper by the same authors, I think, refers to the fact that binary translation gave them very good performance, and even with comparing it to some of the hardware architectures, which I'll do later, I think it gave better performance on some of the things, especially with memory page faults and things like that, because you could avoid a lot of the faults and do direct put direct hooks in the code. Even in integrity HPVM, which we were handling here in HP Enterprise in India, I think even Rashi here, who's on the call, is one of the experts on that team. And we also did a very similar kind of model where we had binary translation for a lot of places in the code, which we couldn't handle. Privileged instructions, and then most of the instructions would fall through directly, so it will be a direct kind of translation. But there would be places where we had to do binary translation to handle it. So this was a big technique, I think, to solve the problems of the fact that x86 processor could not be virtualized directly with trap and emulate kind of concepts. And then the second method of software virtualization which was used was actually made famous by Zen. So Zen had this concept. I think it was, again, like I said, it was a type 1 kind of hypervisor. So the virtual machine monitor would run directly on the hardware. But then they had this concept of a domain 0, which would be a also be a guest OS, but it will be a slightly more privileged kind of guest, which is running a Linux, for instance. And it was the one which would kind of manage the IO devices. So in fact, I'll talk about more of the IO virtualization challenges, I think, coming up. But in the older architecture like VMware, which I was referring to, I think the OS virtualization would, I mean, the OS handling, the IO device handling actually would happen within the host operating system itself. I mean, where it was a type 2 kind of architecture where both VMM and host were running side by side, and you could actually run the IO devices from the drivers from the host side. But in the case of Zen, I think what they did was they had the IO devices being managed from the domain 0, and then they had multiple VMs which they could run on the VMM, and the VMs would then talk to domain 0 to talk to an IO device. So anything IO which is so for instance, if there's an Ethernet card which is trying to talk to a particular VM1, it would be intercepted by the VMM, and the VMM would transfer the control to domain 0, and then the domain 0 would have a communication. So it's called backend. So from the domain 0 to the VMs, there would be a communication backend, front end driver kind of communication to be able to actually get the data. So this was what Zen did in terms of IO handling. The other thing which Zen did was para virtualization. So they modified the VMs. So it was not the standard Linux. It's a Zen Linux which is running on the guest VMs. And wherever there is code which requires special handling and can't be handled with a trap and emulate kind of architecture, they would kind of do a para virtual call basically into the VMM and handle it there. So it was kind of uh, direct calling into the VMM to be able to handle some of the uh, privileged kind of execution calls which are there. So this was the second approach. So both approaches were kind of popular. I mean, the binary translation and the para virtualization. But I think both of them kind of added performance overheads. I mean, there was always uh, the problem that some of these things, because you're intercepting them and doing all the translation, it takes a lot of time. And so the performance of the initial virtualization solutions was not very good. I mean, it was not acceptable for an enterprise level, especially. And that's when we started to, I mean, Intel and AMD and other processors started to look at hardware virtualization techniques. So before I move into hardware techniques, so this what I talked about just now was the CPU handling of it. Memory, on the other hand, I think memory virtualization was done through what is known as shadow page tables. So the issue which you have is that a VM, when it accesses a virtual address, it's called a guest virtual address. So let's call it a GVA. And the OS within the VM would do the translation from a GVA to a guest physical address, a GPA, using its page tables. But then that guest physical address has to be different for different VMs. So it has to be the VMM ensures that each VM gets its own guest physical address space, which is kind of unique. I mean, which is actually unique from a host physical address perspective. But each of these VMs can actually use the same guest physical address. I mean, internally they could be talking, let's say, to a hex 8000 or something like that as a physical address. But then that guest physical address needs to be translated to a host physical address, which could be different locations. So even though they are the same location within two VMs, for instance, I mean, if you run the same Linux operating systems on both the VMs, you will see that the addresses being used during startup are pretty much identical on both, but they are guest physical addresses and they need to be translated to a host physical address, which is also called a machine memory in this case. So in this slide, you basically see this green part, which is the machine memory, which is getting translated into physical addresses on the VM side, which are called the guest PAs. And then the processes are using guest VA to be able to access guest PA. Now, the challenge which happens is, I mean, as far as the OS is concerned, it will try and write to the CR3 register and say that these are my page tables, and this is how you go ahead and do the translation. But then it can't really write to the processor CR3 with those page tables, because then it could two VMs could kind of overlap and there could be an issue. So the VMM needs to ensure that the actual page tables are different. I mean, so when they're running on the actual hardware. So the way this is accomplished by VMMs is by something called shadow page tables. So the guest maintains a translation from a guest virtual address to a guest physical address space as it does normally. And then the VMM maintains the actual translation from a guest virtual address space to a host physical address space. And the CR3 of the actual processor is inserted by the VMM. So if a guest kind of OS kinds of tries to write to CR3, it will be intercepted by the VMM, and the VMM will make sure that the correct CR3 is there and it is not allowing it to be overwritten with the what the guest wants to write. So that's how virtualization is done. So this method is called shadow page tables. So basically the VMM is maintaining a shadow of the real page tables, which translate from the guest virtual address space to the host physical address space. And so if you see how different people handled this problem, I think they handled it slightly differently. Like the shadow page tables were very popular in VMware and other architectures, where if the guest tries to modify any page tables, you have to actually sync it to the VMM shadow page table, and that's not easy. I mean, in the case of VMware, for instance, if a guest operating system is trying to write to some page tables, it's not really protected by anything. It can actually go and write. So how do you trap into that? So there is a whole architecture around memory tracing in the binary translation part of it, where VMware makes sure that it traces memory and then figures out where page tables are being written and then kind of intercepts them and then writes to the actual shadow page tables and maintains synchronization there. So it's a pretty uh, advanced architecture, and it's not very simple to talk through probably in a single session. But yeah, I think there is literature on it, so maybe you can go through it. Zen, on the other hand, does it kind of differently. I mean, what Zen does is that it actually gives the CR3 to the guest itself, in the sense that the guest, when it tries to write to the CR3, which is the page directory, it allows it to write to it. But then whenever there is a page table getting added, the guest has to do a para virtualization call. It has to call into the VMM saying that I'm creating this page table entry, and that's how the VMM maintains kind of consistency and makes sure that the guest is not writing into something which it is not allowed to. But basically, it allows a full level translation. So the CR3 is actually a translation from the VA to the MA, and that is allowed through para virtualization by Zen. So these were two software techniques which were used for handling how memory had to be divided among operating systems and how consistency had to be maintained in the physical addressing which they were doing through their page tables. So that's about CPU and memory in terms of software techniques which were being used. On the I/O side, I think there were multiple again models. Like I said, there was this monolithic model where the hypervisor could actually manage the I/O drivers and the I/O services, and it would basically have the IO drivers, but it would mean that the hypervisor has to write all the drivers again. I mean, which the operating system would have already done. But you had to write those drivers again. You had to maintain them again and release them. And so there, but it had higher performance because you could actually optimize it for the architecture and where you had the kind of performance issues. But this was not very popular. I don't think many people adopted this approach. So the other approach which Zen adopted was um, the like I said, the domain VM concept, right, where they had the domain VM DOM0 actually managing the drivers, and then the guest VMs would talk to the DOM0 to be able to talk to actual devices. The third method, which is not mentioned here, is where you could have like a guest operating, which is like used by VMware GSX and maybe even HPVM and KVM and others, is where there is a host operating system which comes up on the actual hardware. It kind of maintains all the drivers and as it does normally, like a Linux operating system, and then the VMM runs within the Linux operating system, and it's a kernel module which kind of talks to these devices. So that's the third model which is not shown in this diagram, and it's also a pretty popular one, especially with KVM and QEMU when you start using that approach, and we'll see some of that in the demo also, I think. The so yeah, like both of these all three of these architectures, I think, had performance issues. I mean, it was not easy to virtualize because you had to virtualize the IO, and then there were performance penalties since you had to make transitions from the guest to the host and then to the actual device, or from the guest to the VMM to the device. So this was the major bottleneck when it came to virtualization. I think IO became the major bottleneck. CPU and memory were kind of not as huge a challenge in terms of performance. So that's when people started thinking of the pass-through model. So where you could directly assign IO devices to the guest operating systems. And I will talk about technologies like SRIOV, which came up in the PCI SIG to be able to handle such kind of direct assignment of IO devices. So yeah, so to kind of summarize, I think these were the challenges which we saw, and then we saw how software architectures were used for handling CPU, memory, and IO virtualization. But as I said, like since most of this work is done in software, I think the performance overhead was pretty high, and so using virtualization for enterprise use cases was a challenge. I mean, it used to have a huge performance overhead. So next we will look at hardware techniques for virtualization. Before that, are there any questions? So if there's nothing, I think we'll move into the hardware techniques for virtualization. So I think this is more contemporary. Uh, I think the lot of these techniques which have come up over the period from 2000 period, but I think some of them, I think typically with hardware techniques, I think things get either they go away over a period or they kind of become commonplace. I think in this case, I think yeah, they have become commonplace, so they've not gone away. But typically, a lot of hardware technologies kind of disappear also, like the weapons technology mentioned here. So, like I said, I think CPU virtualization, I think, was the first thing which was tackled by AMD and Intel. I think around 2005 timeframe, they came up with the hardware support for virtualization. In typical IA32 operation or the x86 operation, you have these two rings, 0 and 3. Like I said, in 64-bit architectures, 1 and 2 kind of go away. So it's more of a 0 and 3 kind of architecture, which is there, the user space and then the privileged kernel space or privileged space. And what Intel introduced is they introduced new instructions, and they introduced a whole new operation called a root operation. So VMX root operation was created by Intel, which you could enter that root mode through something called a VMX on instruction, which was run from ring 0 when the system was had booted up. And then from there, once you are in that root operation, you can actually launch guest operating systems with another instruction called VM launch. And VM launch would launch a guest operating system along with its applications in a separate non-root, what is called a non-root kind of operation. So it kind of it's like a layer of abstraction which they provided with this root and non-root hierarchical kind of rings which they have provided. And within that non-root operation, the guest would run again in it could use anything from ring 0 to ring 3. So it was like a normal guest operating system or normal operating system running on the bare metal, where it could use the operating system kernel for ring 0 and the applications in ring 3. So this allowed it to kind of become like a normal architecture, and it became very simplified in terms of running guest operating systems. So a VM exit, on the other hand, would take the operating system to the guest operating system into the root operation, and this was required for virtualizing some of the things which still needed to be virtualized by the VMM, because not everything is handled with just the CPU instructions. So I think there are things which still needed to be virtualized, like memory and IO and interrupts and things like that. So everything which needed to be virtualized needed to have a VM exit coming back to the VMM, and then the VMM would take action on that. And a VM, once it had taken that action, it could VM resume and then take it back to the non-root operation, where the guest could run as if it was running on a bare metal kind of hardware. And like this, you could run multiple operating systems. The VMM would maintain control of everything, and it could launch the guest operating systems as it wanted. So this was a hardware virtualization which was introduced by Intel, called virtualization technology X for VTX. For they had a similar concept of VTI for Itanium, and initially they called it Vanderpool technology. I think over time it changed into just virtualization technology, I think. And the other thing to note in this is that for each of these guest operating systems, the processor now maintains a control structure, what's called a VMCS, a virtual machine control structure, which handles all the virtualization part. So if the VM is trying to do a privileged operation and it exits into the root operation, then the information about that is maintained in the VMCS, and then the VMCS actually maintains the metadata for virtualization for the guest operating system. The VMCS is typically a memory mapped kind of structure, so you can actually do load stores to it from the root operation. From the non-root operation, you don't have access to the VMCS directly. So, like I said, the new instructions VMX on and VMX off to enter and exit the root mode, launch to launch the guest, resume to resume after an exit, like I said, to transition from the guest to the VMM. When you do a VM exit, it saves the guest state in the VMCS, and it would have uh, saved also a VMM host state in the VMCS. So it will load that so that the host starts running, the VMM starts running, and then once it resumes back, it would again say relaunch it from the guest state which it had saved earlier. There were some other instructions like VMPTR ST and VMPT store and load to read and write the VMCS pointers, and you could even do read write VM clear, I think, to read write and clear a VMCS. And finally, I think it also introduced the concept of a VM call. So like I said, in para virtualization, you have guests actually calling into the VMM, and this new mode made it easier by creating an API called VM call, wherein you could do para virtualization. So the guest operating system could directly call into the hypervisor where it needed to, if it needed some kind of optimization in some code. So this was yeah, I think this slide basically goes into more details of some of the things in the VMCS which it saves. So for instance, the guest save state, you'll have the processor state saved on VM exits. It'll have things like the instruction pointer where it kind of exited into the VMM, the stack pointer, all these things, the whole context, register context, to be able to restore it when it starts running again. Also the system state, processor state, things like E flags and segment registers, IDTR, all those things are saved. The CR3 register and all that is saved when it goes into the guest save. Similarly, host save, I think, will have the processor state loaded for VMM to start running once the VM exits into the guest state, and how the VMM can start running. So all these things are maintained in the VMCS structure. It's a 4K table for every guest, and it works pretty well. I think it's been used by almost all the virtualization vendors since it was launched, and everybody has hardware virtualization support today. So just to go back to the old slide, which I talked about the challenges, I think now those challenges kind of go away because the guest kernel and the guest app both get their own rings. I think they can run at ring 0 and ring 3. And so all the instructions which were earlier privileged and we had kind of issues with them running, I mean, the sensitive instructions are no longer sensitive. I think even the system calls will now go from the guest application into the guest kernel and not really to the VMM, since it doesn't even know that there is a root mode or a non-root mode which is existing. So this root mode which the VMM runs in is also called ring -1. So I guess the lord of all the rings, I guess, in a sense, and that's where the VMM maintains controls of it. Yeah, and there's a clean context switch on VM entry exit from uh, because it goes from non-root mode to the root mode when it switches to the VMM. So it solved all the problems which are there. I think it basically made the x86 architecture virtualizable and made it kind of allowed the trap and emulate kind of architecture which Goldberg and Popek were looking for. So this solved the CPU challenges which were there, I think, in terms of instructions and their privileges and sensitive instructions. But then memory, we still had an issue. I think we still had to have shadow page tables because we don't know when what a guest OS or a guest kernel application is doing to memory, and when it is creating page tables and things like that. I mean, can it overwrite some other physical address? So all that kind of consistency still needs to be maintained by the VMM. So like I said, it used shadow page tables and in the Zen case, the writable page tables to be able to solve some of those problems. So and that again was a performance overhead because you had to intercept all those writes, you had to trap into the VMM, and or you had to have binary translation to be able to figure those things out, or you had to have para virtualization like in the Zen case to be able to handle those things. So all were huge performance overheads. And so in 2008, Intel as well as AMD both came out with enhancements in their page table architecture called Intel called it enhanced page table and AMD called it nested page tables, NPT. And the idea was that the guest would actually load the CR3 with whatever it wanted. So it would load it with something like a GCR3, which says it's a guest CR3. And then, but the hardware would do the actual hardware walk, and the VMM would set up the an EPT or an enhanced page table, which the guest would use to do the translation from, which the processor would use to do the translation from the guest linear address to a host physical address. So what the VMM had to do is it had to set up this host CR3 kind of mapping to be able to do the translation from guest physical address to the host physical address. So it's like a kind of a hierarchical thing where you can do one level of translation from the guest linear address to the guest physical address, and then the host CR3 would take care of doing the second level of translation. But like in a standard page table design, all this happens within the hardware. So it's a hardware walk. So the processor takes care of doing this whole page table walk, and all the software has to do is basically set up the page tables. So in that sense, it's pretty neat, and only one time the uh, VMM has to set up the page tables for a particular guest, and then everything is taken care in terms of when it runs. And yeah, so this basically caused a significant reduction in the exit frequency. So you don't have to exit on any page table modifications. You can modify it within the guest. I think it's as fast as native, and the page faults would require no exits. Context switches would require no exits because each guest could just load its own CR3 and start running with it. So it was pretty transparent in that sense. But one issue was that it did result in more expensive TLB misses, because once you so the TLB, I mean, I'm not sure if you talked about this in the first week. I think the TLB is called the translation locusite buffer. Basically, it translates. It keeps a cache of the mappings of virtual address to physical address, and the processor maintains this. And so if something is not in the TLB, it has to do this hardware walk. And so whenever you miss something in the TLB, it's called a TLB miss, and so you have to do a hardware walk to be able to get to the actual address. And this causes a major issue with especially application startup, right? When you have a fork of an application and it starts up, you see a lot of page faults which are happening when it starts up. So all those page faults, I think every page which gets created, I think it'll have to go through this kind of translation before it gets into the TLB. So an application process startup would be pretty expensive on this architecture. And Yeah, I think so. So one of the ways that this was solved with is another hardware feature, which was called address space identifier in AMD and virtual processor identifier in the case of Intel. So the way I think it kind of seems logical. If you see the TLB today, it has a translation from a virtual address to a physical address. What they did is they added one more field saying that this is the this entry corresponds to which address space. So the address space basically is the VM or the guest which is running. So if guest 1 is running, it will have its own set of TLB entries where, kind of tagged with G1. Guest 2 would have its entries tagged with G2. And so the hardware would know that, okay, if the guest G1 is running, then it needs to use this entry. If it finds the same entry in another guest, then it knows that it should not be using that. And so those are the kind of things which are done. I mean, the TLB is pretty small. I don't think it's too big, and so that's always a challenge to be able to maintain the amount of entries in the TLB, and that's one of the optimizations which was done. Otherwise, what would happen is every time you have a VM exit and then another guest starting up, you would have to flush the whole TLB. I mean, you'll have to basically remove all the entries and then restart the guest with the and it would, as soon as it starts up, it would start hitting faults, and it would again, I mean, have the TLB misses will have to be converted into the entries. So that's always a challenge. But with this, I think you never didn't need to do a flush TLB purge, as it's called, when you do a context switch, and you could keep the entries as it is in the processor tables, and then because they are tagged by your guest information. So this was another neat enhancement which came after the EPT and NPT. So just to go into a high level view of how the translation looks, I think this will give you an idea of some of the performance overhead of this. So when you have a standard unvirtualized x86 translation, you have a virtual address which comes to the CR3, and then you have, like we talked about, you have parts of the virtual address indexing into the page tables, the directory, and then the page table levels from 4 to 1, and then you finally get the address. And so you have basically 4 memory accesses, because you have to access each of these levels: page PML4, the directory, and then the page table entry, and then the page table entry finally. So there are 4 memory accesses which have to happen for a unvirtualized x86 translation. But now if you go to the same thing for a guest with EPT, it becomes much more complicated. So a guest virtual address, when it has to be translated from the CR3, the CR3 itself is, like I said, it's a guest physical address. So you will need to translate it through the host page tables which the VMM has set up. So that goes through the first level translation of the CR3, goes through the host level tables, and it has to go through that 4 table walk, and then it comes out with an address which is corresponding to the host this thing. And then again, that page table, you have to index it with the GVA. And then once in that page table, what you see is, this is actually, as you can see within that yellow box, is basically the guest space. So again, what you see there as that entry within that level 4 is a guest address. So again, it has to get translated, guest physical address. So again, it gets translated through the host tables, and it takes 5 memory accesses for that. So you see that each level, as it goes through, you see that it has to go through a hierarchical kind of translation. And finally, the memory addresses, the accesses which is happening is around 24. So it's, even though it's simplified things, I mean, it gets taken care of transparently behind your backs. It is a very expensive hardware walk operation. So it takes 24 memory accesses for the processor to actually get this. And even though a processor can cache some of these things, I think it can still be pretty expensive, because it cannot cache for all the guests at the same time. So this was one of the major challenges with EPT in terms of performance overhead, and there has been a lot of work in this space to be able to improve the performance of this. I think I may have a pointer in the end of the this thing on references, where you can go back and see on some of how people have kind of tried to solve this problem with some kind of direct translation in some cases, and some kind of partial segmenting and partial paging and things like that. So I think there are interesting papers on this. Okay, so I talked about VPID. I don't think there's much to talk about on this slide, except to show that this basically is showing how it looks. So the idea of a tagged TLB is that, I mean, each TLB entry is tagged with an identifier of the guest, and it allows it to not get flushed when switching. When do your context switch is not so expensive. And so you can just see the processor sees the VPID and decides if it can use that translation safely. And you can activate this with again a control bit in the VMCS called enable. I think it's VPID, not VPIP. So you could. It's a pretty simple way of setting it up. So that kind of solves the memory problems in terms of hardware virtualization. So everything now what you've seen is that CPU as well as memory, everything is taken care of by the hardware, by the processor, and all the VMM needs to do is to set this up one time. I mean, it needs to set up the VMCS, and then it needs to set up the EPT page tables, and then it's done. It just needs to launch the guest, and we can start running. But then IO is still an issue. I mean, IO is, like I said, uh, typically the way virtualization was done is, I think an IO device would be shared among multiple guest operating systems, and so that virtualization would happen either in a host or in the hypervisor, and that requires a lot of interactions with the guest and a lot of interceptions which have to happen before the IO requests get communicated either side. And so in 2012, I think Intel came out with what is called the VTD architecture, which stands for Virtualization Technology Direct IO, where they came up with the architecture where you could actually have devices directly mapped to a operating system, guest operating system, and it could directly write. So the challenge before that was you could assign a device directly to a guest operating system, but then how do you program it? If the device is programmed with guest physical addresses for DMA, it cannot do DMA to guest physical addresses because they are not understood by the processor itself. So when it puts out an address on the memory bus, CPU memory bus, saying that do a DMA or a direct memory access to this particular address, the processor doesn't understand a guest physical address on that side on the bus, so it doesn't know what to do with it. So that's the challenge we had with doing kind of pass through direct IO with earlier virtualization solutions. So with VTD, what Intel did was that you could actually set up this remapping engine. So similar to the page tables which we saw with memory, you could have a remapping engine to map from a guest physical address to a host physical address. So you could have the translation set up, and this was basically set up again in the processor, and you could set it up basically for each of the devices. So if you understand PCI and how it works, I think PCI on the PCI bus, each device has a bus, a device, and a function associated with it. So with that bus device function, you could associate saying that this particular virtual address or this particular guest physical address has to go through this kind of mapping to be able to get a final physical address. And so you could have, so this was also called an IOMMU. It's basically like a memory management unit similar to the CPU, but it's on the IO side. So it was called an IOMMU, and you will see that terminology a lot in literature, I think. Even though I think AMD is the one which called it an IOMMU first, but I think now everybody, I think, uses IOMMU more frequently than Intel's VTD. But they're basically the same concept. So you could basically translate from a guest physical address to a virtual physical address, to a host physical address. And you could have this kind of mapping table maintained by the VMM, where it says that for every bus device function, this is the walk which you need to do to be able to get to a particular address. And so one thing which you would think of is, I mean, if this is similar to the MMU, why is this different from the MMU? So that was one thing which AMD I think also thought of, and I think they had some concept of where you could kind of leverage the MMU setup for the host translations for the IO also. So, but yeah, I think in Intel's case they kept this separate, and so you had to set up both these things independently. The other thing which they introduced with VTD was this translation cache. So once you do these mappings, right, I think like I said in the previous one, like you saw, I think these are expensive operations. You have to do this hardware walks every time. So instead, once you do a walk, you can cache it into the remapping engine itself. So it maintains a translation cache of entries so that it can do a fast translation whenever there's a frequent access to a particular address or something like that. So this again helped a lot in kind of pass through kind of IO, where you could assign a full NIC card or a full storage card, for instance, on the PCI bus directly to the guest operating system. And if it tries to access a wrong address, or if that address does not belong to that particular guest, for instance, I think you can generate a fault. So and that can be handled through a machine check architecture or something like that on the processor side. So yeah, this is just another slide which talks about the VTD hardware page walk. So I won't go into details of this, but I've already talked about it. Based on the bus device function, you have these assignment tables, and then you can do a similar walk like a memory walk to be able to get to the page. So any questions so far? Probably moving a bit fast. Okay, maybe we can take questions at the end also. So like I said, this was pass-through IO. Basically, this was the first stage of pass-through IO where you could directly assign a IO device to a VM. But then if you have a standard PC or a server also, I think if you see a smaller end server, for instance, how many IO devices, PCI devices do you see on it? You'll probably see maximum around 8 to 10 PCI devices or something. So now if you start assigning PCI devices directly to a VM, then you are going to run out of them. I mean, you cannot assign all of them to independent VMs, especially if you want to run things like 200 VMs or something on a single system, which does happen. I mean, people do run a lot of VMs on systems, and so you cannot really give one IO card each to one VM and typically one IO card is also not enough. I mean, you'll need a NIC card, you'll need a storage card, you need maybe a graphics card or a GPU or something like that. So it's not feasible to be able to you directly assign IO to a guest operating system. So what PCI SIG, which is the special interest group for PCI, did was they came out with this technology called SRIOV, which stands for Single Root IO Virtualization in 2016. And what this basically means is that when you have a single PCIe card on the PCI bus, it can be divided into multiple what are known as virtual functions. So like I said, a PCI device typically has a bus device and a function associated with it. That function is what is known as a physical function. But for a SRIOV device, you can actually have multiple virtual functions beneath that single physical function. So it's a very interesting concept, and this SRIOV configuration can be maintained by the VMM. It can actually do the configuration or the host operating system, and then it can assign these assign these virtual functions to a particular guest. And we will see again an example of this in the demo session when Rashid talks about it. The other thing which PCIC came out with at the same time was multi-root IOV. This never took off for some reason. I think they had this idea that you could have a shared topology where you could have an MRIOV device maybe outside the box, and then it could actually talk to multiple systems or blades, and they could share that topology. So even though this seemed very exciting at that time to be able to do shared kind of IO across multiple systems, it somehow never took off, and I'm not even sure if there are any devices with this capability today. So yeah, so this is yeah, we'll not talk about MRIOV. So SRIOV will is what kind of became popular after 2016, and I think in the last 4 to 5 years, I think you will see that there are quite a few cards which have implemented SRIOV today, especially on the networking side. I think you will see that most of the Mellanox and the other cards around 100 gigabit Ethernet, 200 gigabit Ethernet, the smart IO cards which are coming out now with Pensando and others, all have the SRIOV capability to be able to support multiple virtual functions, so that they can be assigned to multiple guests and independently. So even with SRIOV, I think there was still one area which was a huge performance overhead, and that was interrupt virtualization. So when a device actually tries to send an interrupt to a system, I think that cannot now directly it goes to the host, and the host needs to do the virtualization of that. So that is a huge area of overhead. And this slide, I think, was from I think Jun Nakajima, I think, of Intel, I think, who I think had done a lot of work on some of this interrupt uh, enhancements in virtualization. And he showed that in Zen, I think some NetPerf is a standard benchmark of networking, where you can run multiple networking TCP streams and see the performance overhead. And he showed that I think the number of total VM exits which are occurring because of each of these interrupt virtualization features, he showed which ones take the lot of time, and you can see that external interrupts takes the maximum time. And so basically interrupts which are coming from the device to the system, even though they are expected to go to the guest directly, they cannot go to the guest. They come to the host, and the host has to do the virtualization. So that is an area where there has been a lot of enhancements recently. um, Intel has also introduced something called APIC virtualization, APIC V. APIC stands for basically the advanced programmable interrupt controller. So it's basically the device within the processor which does the interrupt handling, and actually listens to the interrupt, and then wakes up the CPU and tells it which vector to branch to and things like that for that particular device. So that now needs to be virtualized. So there was a lot of work done to virtualize that. With Intel, it's called APIC V. With you will see things like GIC on the ARM side, where they have done GIC virtualization for the interrupt controller. So this was again another area where they did a lot of enhancements to be able to improve the performance. In the case of so Epic V wasn't kind of sufficient, so they also added things like posted interrupt. So in the Broadwell CPU of Xeon, I think Intel added support for posted interrupts, and you can see an idea of that before on on how things were working, right? I think on the left hand side, if you see typical handling, it would have external interrupts would have come to the VMM, and then it would have had to be delivered through a software Epic V model to the guest operating system. And so you would have seen all these VM exits and entries happening when you get interrupts. With Epic V, a lot of this was kind of streamlined and handled in hardware, where you could the VMM would still receive the interrupt, but it could kind of pass it to the Epic V, and the Epic V would do the handling. The challenge with the first approach compared to the second is that in the first case, the VMM has to know exactly when the guest OS can receive an interrupt, for instance. It needs to know the guest OS, for instance, in some pieces of code would have turned off interrupts, but the VMM will not know that unless it traps and emulates everything, every such access, which is again a performance overhead. So instead, I think this Epic V approach kind of streamlined things, because all the VMM had to do was update the Epic V, and then the Epic V would ensure that the guest OS gets the interrupt when it is ready to receive it. Excuse me. And then with posted interrupts, this was improved even further, I think, where I think the VM could actually post some of these interrupts to a queue, and then the external interrupts could be directly delivered to the guest operating system. So this also used another feature in VTD. So they came up with something called interrupt remapping, where interrupts have also evolved over a period. So I mean, in the older technologies, where you've probably read the older legacy systems, interrupts used to happen through pulling a particular line. But in modern day systems, interrupts don't happen through that mechanism. They instead happen through a messaging kind of architecture. So an interrupt, when it comes into a host, it's also actually targeting a particular epic. So it's targeting a particular address, the address of that CPU's epic. So once it comes in, once a VM configures the device, the device would actually do a try to do a interrupt to a epic V address, but then that needs to be translated by someone. So again, VTD had this concept of interrupt remapping, where it could remap these messages to be able to directly go to the guest operating system. And with posted interrupts, I think it could be done whenever the guest OS is ready to receive an interrupt and things like that. So a lot of enhancements in this space to reduce the number of VM exits. There still are exits in this space which have not been resolved completely. I don't think that has been possible, but it has improved the performance substantially. And nowadays, I think virtualization performance kind of compares pretty favorably with bare metal performance. It's probably of the order of 5% in most workloads or less, and only in certain cases it kind of goes above that. And yeah, I think that kind of completes the enhancements which were there. I just put in a bullet on nested virtualization. It is another area where there has been some work in the past. So nested virtualization basically means that you can actually have multiple levels of virtualization too. So if you can have a guest operating system, and then you can have virtualization within the guest, where it can spawn multiple guests on its own. And this is I felt it was more like a cool feature which you could have. It was probably not as useful, though I think they felt that it was useful in test and validation kind of environments, but it was not really an enterprise scenario. So I don't think nested virtualization has really taken off too much. I mean, it is there eh, in these things, and you can try it out also. In fact, I tried it out a few days back, where I could on a VirtualBox guest, I could actually, I just had to enable a few settings in VirtualBox for nested virtualization support, and you can actually go and so on your Windows laptop itself, you can have VirtualBox and start a VM, and then within the VM you can start a QEMU KVM guest, for instance. So it's pretty cool to see, but yeah, may not be of much value beyond that. Um, yeah, I think that pretty much covers most of my slides. I think this slide basically shows that both Intel and AMD kind of did the same things around the same time frames. Intel probably was leading in most of them. I think they came out with VTX first. AMD called it SVM. Then they came out with what was LT, was I think the Lagrange technologies. Not, I don't know much about that. I think it's some security stuff. And then VTD, the IOMMU, and the extended page tables, the VPID, and then more enhancements for the IOMMU. I think VTD2. So the VTD was on the basic IOMMU. The VTD2 was around the interrupt remapping and other support, I think, which came in later. And AMD went on its own path. I think similar things with SVM, SVM2, and then IOMMU, and ATS, which is the address translation services, and then SVM3. I don't know. This is an old slide, so I'm not sure. Probably a newer slide would give a better picture of like what has happened after that. And yeah, so future trends. In virtualization, I'm not sure what's the next barrier to break. I think the IO performance is still an area where people are continuing to work and trying to see if IO and interrupt performance can be improved. So you will still see some papers in that area in the recent past. Memory also, I think some of the translation overheads are still high with EPT. So there is probably some work going in that area. But I also feel that virtualization is kind of hit its peak, and we are now into the era of containers. And even in fact, even in containers, there are people who have tried to use some of the memory virtualization techniques like EPT to be to be able to kind of separate and isolate the containers. So there's still use of these technologies as you start to look at some of the newer technologies like containerization. And I think you will hear more of that in tomorrow's talk from Raman on containers and Dockers and Kubernetes and where the world is going with some of those. But like I said, yeah, I think you should be able to use some of these technologies going forward with that also. So I think it should be still an exciting time. That's all I had. So are there any questions before we go on to the demo hands-on lab, which I think Rashi will handle. Rashi, you can let me know how to handle that. But before that, let's take questions. So I had to rush a bit. Sorry about this. This is a very heavy topic. I think there's a lot of information, a lot of slides. I don't think I can do full justice to it, but I hope I've given enough of an idea that you're excited to learn more, and you can actually go back and read some of the literature. So I have yeah, one more Calvin before I get into the last part. So I hope what I did was not like what Hobbes felt in this cartoon. But one final slide, I think, yeah, which I didn't talk about. I think if you look at this, I think like told earlier that I mean the old technologies seem to keep coming back. So what VT calls non-root mode and AMD Pacifica calls guest mode was called interpretive execution on the IBM VM370 and the mainframes. So it was called SIE. And so yeah, like the second one says, VT's launch instruction was called SIE in IBM. VMCS was called as state description on the IBM machines. They also had shadow translation tables and a dual page table walk-in hardware in IBM back in the 70s. So you can imagine. So a lot of it in x86 has come only now. So it's very interesting. And finally, they also had an interpreted SIE for nested hypervisor support. So which is, like I said, slowly maturing on x86. It's still pretty new. And yeah, I think the final slide, these are the references. I think the one around the Popek Goldberg one is more for mathematical folks, in my opinion. The Robin Irvine one would give you a very good idea of the Intel instructions and where the challenges are. Adams and Agassiz would give you an idea of all the binary translation and all the nice stuff which they did. I think the next two, in fact, including this one from Agassiz and others on software techniques. This is a much older paper from Bugnion. Like I said, Bugnion, Devine, Rosenblum, all these guys were later in VMware, but they originally did all this work with something called Disco, which is also a very interesting early paper. So you can get the early challenges information from that. Rich Ulig, Gil Niger, and others from Amy Santoni and others from Intel, I think, wrote the original Intel virtualization technology paper, and that's also an interesting one. This one talks about EPT and how we can handle some of the issues with the dimensionality of the nested page walks, which we saw, right, in terms of 24 accesses to memory and how we can improve performance of that. And this one talks about nested virtualization. So interestingly, this paper is called the Turtles Project. So there's some joke around this where I think someone says that who's holding up the world, and uh, someone answers that it's a turtle, and then who's holding up the turtle? Then the other person says it's turtles all the way down. So I guess nested virtualization is like that. So it's turtles all the way down. And then you have Eli, which is exitless interrupts, which is basically around some of these challenges with interrupt handling. And this is also a very nice paper. I think it was implemented in KVM also. And the last one is also again around direct interrupt delivery at around 2015 timeframe. There have been newer papers on some of these things. I've probably not looked at them in the recent past because I've not needed to for my work. But I think you should definitely go and see these papers and see the other papers which cite them, for instance, which are newer, and maybe see what's happening in this space. So I would encourage you to do that.